I don't know. I don't know.
I never can really make
Okay. You want to do that? You want to do that now?
I can do it now, or I can do it during 8th period.
Either one is fine with me.
I'll just do it now.
Okay. Fine. Hang on just a second. Let me pause this. Okay, so let's look at yesterday's warm up. And yesterday's warm up is a preview of what's coming over the weekend, hopefully, if I can get the video made. The purple shingles on your desk. I do not have a good video for that. I have a very bad video that's an old one, but I want to redo that. So if I can do that during 8th period today, I'll be able to watch a video to fill in the blanks on that. It will probably be a long video, so I don't know. I may just say watch the first little bit to kind of I don't know. We'll see. I may even break it up into 2 videos. But this is something called a power series. It is a series that has an extra variable thrown in, and with power series, we'll be doing a lot of these. As a matter of fact, the majority of series questions on the AP exam are power series, where you have like this extra X in there, which opens the door for a lot of other questions. And the most common question is find all the values of X for which this series converges, which is also known as the interval of convergence, which you'll learn later. And in this case, what's the trick? What kind of series are we looking at? This is a geometric series with a ratio of X over 4.
I'm not sure I understand.
We need to keep track of how many times it does that. And a geometric series converges when the absolute value of the ratio is less than 1. And so we need to determine when is the absolute value of X over 4 less than 1. Well, that's going to be when X over 4 is between -1 and +1, which is when X is between -4 and +4. Or you could answer that in interval notation as -4 to +4. Or you could answer it in international interval notation, which is -4 to 4. I love that notation. I wish we would adopt it. Yeah. Yeah. The only reason you don't like it is because you're not used to it. But what's the disadvantage of our system? What does -4 or 4 look like? It looks like an ordered pair, doesn't it? There is no way you're going to confuse that bottom one as an ordered pair, right? Also, for those of you who have crap writing, I see some people whose brackets look like this and whose parentheses look like that. Yeah. Yeah. With the other notation where you point away from the numbers, you don't have that confusion. Yeah. It's a much better. Yeah. And on the AP exam, you should get it right as well. The problem is you're risking a reader not being humble enough to ask somebody what it means and just assuming that it's wrong. So that's the danger. Anytime we as readers see something that we're not sure what it means, we're supposed to ask and keep bumping it up the chain of command until somebody can understand what it is. So, but again, sometimes that slips through the cracks.
This is how I feel. No. That's ASL food,
no. All right. Anyway, by the way, most people do use the standard interval notation. Okay, so let's move on. And I asked you to look at these 9 problems. Did y'all look at them?
Yeah.
Actually, it was 8 problems. 8 problems. And I would be happy if you felt good about 4 of them. Are you going to sit up there the whole time, Phillips? Okay, whatever. That's fine. Doesn't bother me. Just interesting change up. In order of difficulty, I would say numbers. Maybe not in order of difficulty, but the easier ones I would say should be 1, 5. And I'm trying to think from your perspective. Yeah. Now 1 and 5 I think should be the easiest for y'all. I think 6 and 9 are also easy. They're a little bit weird in their presentation, which can be scary. So that's why I hesitated to say those earlier. 2 we actually did yesterday. You remember doing 2 yesterday? Where if you start plugging in values of n, number 2 is your alternating harmonic series in disguise. And I'm not going to go over that one in detail today because I did do it yesterday. 2 does converge, and it actually converges absolutely. That is absolute convergence. And I'm going to go over number 8 really quick. 8, I imagine y'all found that to be one of the more difficult ones. Did you? Okay. The limit as n goes to infinity of 1 minus 1 over n to the 2n power. If you do the nth term test, in order for this series to converge, the terms have to approach 0, right? Now, if the terms approach 0, that does not mean the series converges. But if the terms do not approach 0, then the series definitely diverges. And there is a very common limit, and we talked about it yesterday. The limit of 1 plus 1 over n to the n power is going to equal e. The limit they gave us is very similar to that. This is some version of e with a slight alteration. And the more generic, complete limit definition for e, to include the possibility of other constants, is 1 plus a over n to the b n power will equal e to the ab power. And it's one of those limits that you're going to see. You're not going to see it a whole lot, but you're going to see it enough that it definitely will help you to recognize this. So what is a for this one? -1, right? Because that's minus a 1. That's the same as plus a -1 over n. And b is 2, which means this is going to equal e to the -2 power. Is that 0? Nope, not 0. This diverges. Yeah. And that's when I would not have expected y'all to recognize that yesterday, because I think we've talked about it. Maybe this is now the second time that I've brought it back to your consciousness. Yeah. So let's look at some of these others. What about 5? Why do I think 5 is so nice? If you can compare 5 to the harmonic series 1 over k. Yeah, the natural log of k. How does the natural log of k compare to k? It's smaller, right? Right. And if you have a smaller denominator, that favors a larger fraction. And so if this series is larger than one that we know diverges, then this is also divergent. And that's direct comparison. Good. I think all of the rest I may need to do additional work, more work than I have room on this page. So I'm going to copy 1. 1 I said was a nice. Why is 1 nice? Do we know? It is a geometric. Actually, it's 2 geometric series, right? If we get rid of our STDs, by the way, you cannot combine 2 to the n plus 3 to the n. There's no way you can easily clean that up, but we can STD this to 2 to the n over 4 to the n plus 3 to the n over 4 to the n, right? And those are both as n goes from 1 to infinity. I'm going to quit writing this part. And both of those can be rewritten as, so 2 over 4 is 1/2 to the n. This one is 3/4 to the n. And what do you notice about both of those geometric series? Yeah, those both converge. R is 1/2. That converges. R is 3/4. That converges. Right? Oh, but I said I was going to quit writing n equals 1 to infinity. These are convergent geometric series? What does that mean? We can actually find the sum. We're not going to get to do that often, so we better jump on it when we can. Let's do it. So this is going to be a. So what's my first term? Plug in 1 for n. That would be 1/2 over. My ratio is 1/2 plus my first term here is 3/4 over 1 minus the ratio, which is also 3/4. So 1/2 over 1/2 is 1 plus 3/4 over 1/4 is 3. That series converges, and it converges to 4. Right? That's bragging rights. We don't get to do that much. Yes, and this would be absolute convergence. How's life? We need to have a better attitude. Oh, that's even worse. Cornette, what did I do to hurt you?
It's not you. Yeah, you were talking the whole unit, and I'm so confused. I'm so lost.
I did what?
I'm so lost.
Hey.
Like,
I know. Everybody's always lost in this unit. Y'all are nothing new. I've dealt with this for 18 years.
I'm not ready for this test.
Well, that's good because the test is not today.
I know, but I won't even be ready with it.
Hey, you know what's not helping? Taking 3 minutes out of the day to complain. All right. I had to give the same speech to 6th grade yesterday. That wasn't a speech. That was just a little snarky comment. Anyway. All right, so let's look at 3. We did one similar to this the other day. Do y'all remember it? Yeah. No, we're not going to do inverse trig on this one. Okay. What I see here is 1 over n, right? And that reminds me of the harmonic series. And the harmonic series diverges. So I like to think about some type of comparison to that because I see the harmonic series in the one I'm trying to determine. The problem is the tangent of something is really hard to directly compare to 1 over n. I have no idea if tangent of 1 over n is greater than or less than the harmonic. And because that's inconclusive, what will we do? I don't think that's going to help. No. Y'all, if direct comparison fails, do limit comparison. And limit comparison is when you do the limit of the quotient, of the ratio of those two things. So the tangent of 1 over n over 1 over n. And it does not matter which one you put on top, but you do the limit of their ratio. Now, what do we look for in the limit comparison test? What do we hope to get? A positive finite number. And if I get a positive finite number, what does that mean? No. They do the same thing. If you get a positive finite number, then both series do the same thing. Since we are comparing to a divergent series, then in this case, positive finite will mean divergent. But I don't want you to think that it's always divergent or always convergent. Limit comparison just shows that the two series have the same behavior. We good? So Mackenzie, you did say McCall. Oh, you did say McCall. You did say diverge earlier, and you were correct. But I wanted to make sure we were saying that for the correct reason, that it's because we're comparing to a divergent series. Yeah. So let's do this. As n goes to infinity, 1 over n goes to 0. And what is the tangent of 1 over n? I'm sorry, tangent of 0. 0. And the bottom is 0, which means L'Hopital. So we can look this. So the limit as n goes to infinity. Of the derivatives of top and bottom, the derivative of tangent of 1 over n is secant squared of 1 over n times the derivative of 1 over n, which is negative 1 over n squared. And the derivative of the bottom, negative 1 over n squared. Those negative 1 over n squareds cancel. And now we have, as n goes to infinity, we have the secant squared of 0. What is the secant of 0? It is 1. It's the reciprocal of cosine, right? Cosine of 0 is 1. Therefore, the reciprocal of 1 is 1. And if you square 1, you still get 1. That is positive and finite. Therefore, both series have the same behavior since I compared to a divergent series. Therefore, tangent of 1 over n also diverges. Yeah? Yeah. Okay, moving on. No, there's not. 6. Yeah, I don't think there's anything on the back, is there? Okay, so let's look at this one. It looks kind of scary. Not really. Okay, now that you can do, I wouldn't. So if you, the algebra that you are allowed to do, you can make that n squared times n squared minus 1. Oh, actually, this may work. Have I ever told you that you always put pencil, like you always try stuff with your pencil because sometimes when you actually write things, you think more clearly? I was not going to do this. And I think you had the idea and I was going to dismiss it and I was going to show you why. And I ended up showing you why it's a good idea. So what you can do, by the way, you cannot square root each piece of a difference. Please don't turn this into n squared minus n. You can't do that. That's against the law. But you can factor an n squared out of the denominator of the stuff in the radical, right? Which then, if you have the square root of a product, you can square root the individual pieces. What's the square root of n squared? N? Oh, this is not, okay. Then we have n squared minus 1. And then we have a 1 on top. Are we good? And now I've gone full circle. I'm back to showing that this is not going to be as beneficial as I thought. But that is algebra that you are allowed to do. It does resemble a P-series. So James was very close when he said, can we turn it into a P-series? Technically, no, but we're going to use P-series thought process, right? And so while that is true, I still am not 100% sure whether that will converge or diverge. What I was hoping is that I'll have like 1 over n squared times something. Then it would be very nice, but it ended up not doing that. What we can do is just kind of use our senses here, and we're going to look at the high power terms. These are my high power terms right here. That n squared is going to be dwarfed by the end of the fourth as n gets infinitely large. And so if we look at those high power terms, this looks like the series of 1 over the square root of n to the fourth. What is the square root of n to the fourth? It's 1 over n squared, right? Which that converges. That is a P-series, right? Now, if I wanted to go direct comparison, this series is, how does it compare to 1 over n squared? Because this denominator here, or if I compare it to, if I change my n squared to the square root of n to the fourth, this denominator is smaller than that denominator, which favors a larger fraction. So we're larger than a known convergent series. That's inconclusive. So if you really wanted to kill this dead, if you had to thoroughly prove that this converges, you would need to go limit comparison again. Direct comparison fails, so we go limit comparison, and it'll turn out that the limit is going to equal 1. That minus n squared is not going to be enough to move the needle on the convergence or divergence. That high power term is driving the behavior of the series. And so this one is going to converge. And I'll just say we can use limit comparison. And the end result will be converged. Okay, now good question. Would this be conditional or absolute? Absolute, because there are no negative terms anyway. This is an always positive series. So even if you took the absolute value, it's not going to change the series. So this is absolute convergence. Are we good? All righty. How many more are there? 1?
I don't think they've done 9.
7. Okay. So 7 and 9 are the last 2. Okay. I taught 2 we did 2 in class yesterday, so I just, yeah. Not as part of this sheet, it was like somewhere else. And it just happens to be on the sheet. Hey, where'd 6 go? I swear I copied 6 too. Okay, whatever. 9 I said was a nice one. Why is 9 a nice one? Because sine of n is always going to be between -1 and 1. We can trap that. So if you absolutely value this, it turns into, I know that this is going to be less than the series of n times 1 over n cubed plus 1. And that series is less than the series of n over n cubed, which is the same as 1 over n squared. We have larger denominator. N over n cubed plus 1 has a larger denominator than n over n cubed. This one converges because it's a P-series. with a p greater than 1. And if we keep following our chain of less than, our original series is less than a known convergent series. Therefore, this converges. And this would be absolute. Yeah. The more examples we see and the more we run into, the more, I don't know, the more it'll stick. So I'm going for volume this time. And last one was 6. 7. There it is. So 7, copy, and paste. All right. What do we think of 7?
I thought we did like the one that's AN plus 1 over the N. I thought it was that.
The ratio test?
Yeah.
Ratio test is going to be usually if you see like exponential or factorials. And I actually intentionally did not give you any ratio tests for homework because we had just learned it and we hadn't had a chance to really polish it up. So there's no ratio test in this. There's a trick to this one. What are you saying, Kevin? Okay. If we absolutely valued it, it would turn into this. Well, not equals, but it'll be the sum. And it is a good idea. There's nothing wrong with absolute valuing. I don't know how we're going to determine that convergence, though. I may absolute value eventually, but what I want to do, I'm going to do a cute little trick here. I'm going to leave the numerator alone. My denominator, that's the same thing as natural log of 1 minus natural log of n, isn't it? Natural logs open the doors for a lot of cute little things. What is the natural log of 1? 0. So this is the same thing as negative 1 to the n plus 1 over negative 1 times natural log of n. Yeah. And then I can actually cancel this negative 1 with one of these up here. And this whole series eventually cleans up to just this. N equals 2 to infinity, negative 1 to the n over natural log of n. And now it's a much cleaner, easier to wrap your head around series. Right? So now I'm okay with Camden's idea. Now that I've cleaned it up, what if I did the absolute value of that? Yeah, the absolute value is going to diverge, won't it? Because it's going to turn it into 1 over natural log of n, which is greater than the harmonic series, which will diverge. So the absolute value diverges, but if I did not take the absolute value, would the original series converge? What do we think? You can make a little note that the absolute value diverges. Well, what kind of series is this? Negative 1 to the n. That's an alternating series. So that's an alternating series with the non-alternating part of the series being just 1 over the natural log of n. Yes, sir.
This is coming from me again. The negative 1, how did we cancel out n plus 1?
Okay, because I had what I had was negative 1 to the n plus 1 on top, and I had a negative 1 in the denominator. Negative 1 to the first. Because that's negative 1 times natural log of n. I can cancel this negative 1 with one of those many that are up here, which would be that extra plus 1. Are we good?
Yes.
So back to the alternating series. Once we identify an alternating series, we have to ask ourselves 2 questions. The first one, do the terms approach 0? Does 1 over natural log of n approach 0? Yeah, that's a bottom heavy fraction. That's going to approach 0. And do the terms decrease? Is the n plus first term always going to be less than the nth term? And yeah, that's a slightly larger denominator. That checks out. That means the original series does converge. Now the question is it absolute or conditional? This one's conditional because we established earlier that the absolute value actually diverges. This will only converge if it remains unchanged. How do we feel? Yeah? Yeah? Okay. So what I wanted to look at next are a handful of problems out of the textbook, which, yes, we do have a textbook, believe it or not. First are just a few true-false questions. Those are always nice, aren't they? And sometimes it's good to be reminded of like big picture facts that relate to series. Sometimes we get so busy with the minutia and the details and stuff. And then there are these 7 problems. And I'm not telling you which test to use. I will say that this came out of the textbook section for the ratio test. So we will get some practice with the ratio test today. So most of those will use the ratio test, but some of them will not. Yeah. All right. So what? Yes, ratio test will be on the test. Oh yeah. I missed so many days. I'm not teaching any extra stuff anymore. Anything I teach you will be on the AP exam. There are typically a few things in series that I'll show just for fun, but I'm not going to do that this year. So question 1, if the absolute value is divergent, then so is the original. That is not necessarily true. So otherwise false. It could be true, but for true false, it needs to be a must statement. What type of series would we need to look at that would be the counterexample? Not a specific series. Like, don't give me a very specific one. Okay, an alternating series would be the type. It has to be the word I'm looking for is conditional convergence, right? It's a hard question. I don't know how to ask that question where you know what I'm shooting for. If the absolute value diverges, the original could converge if it's conditional convergence. So that's false. And I could say that this could be conditional convergence. What? Yeah. Is the alternating harmonic series conditionally convergent? That is true. If the absolute value is convergent, then the original is also convergent. That is also a true statement. As a matter of fact, that's one of the tests we use, right? And then finally, if a series is convergent, then the limit of the ratio of the series is less than 1. Now that thing, it's hard for me to read. What are they asking you about on that? They're trying to gauge your understanding of what here? The ratio test, right? Now the ratio test does say that if the limit of the ratio is less than 1, then the series is convergent. The other way of wording that is not necessarily true because there is that inconclusive window for the ratio test. It could be that the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1. It is possible that ratio would equal 1, which is inconclusive. So you don't, I don't know. So that's false. Yeah, that's a sneaky one. Good. All right, and then the examples, the first 3 are the ones where you don't know what test to use. The next 4 are going to be ratio tests. For homework, I want you to do the other 4. And I will, 8th period, instead of recording a lesson for the power series notes that I gave you, I'm going to record myself working these 4 problems. I want you to try them on your own. They're all ratio tests, so try them, and then watch the video if you have questions. And hopefully when we come in Monday, you'll have a chance to have watched the videos and you'll have a better understanding of the ratio test. And maybe we can do power series on Monday. So let's look at 13. First, consider the absolute value. But if you absolute valued it, it turns into 1 over root n, which will diverge because your p is equal to 1/2. And so now I'm considering the alternating series test, which is, does the series of 1 over, does the sequence 1 over root n, does it approach 0 and decrease? And the answer is yes to both of those. And some of these, once you get the hang of these, some of these are going to be very quick mental problems, because that does approach 0. That approaches 0 and it decreases. Therefore, 11 would be conditional convergence. We good? Now, on a free response situation, you need to actually write out the limit as n goes to infinity of 1 over square root of n equals 0. Show some level of algebra or calculus that the function decreases, but that is a conditional convergence. Yeah? Okay, number 13. What's our gut telling us? That is absolute convergence, because if you do the absolute value of the alternating part just makes it always 1 over n cubed plus 1. Well, that's less than the series of 1 over n cubed. Well, 1 over n cubed is p equals 3. That converges. The one I'm concerned about is less than the one that we know converges. Therefore, since the absolute value of the series also converges, this is absolute convergence. Good? Good. Bless. And then what about 15? If we absolute value it, we would have just n over n squared plus 4. The alternating part goes away, becomes always positive. What do you think about that? No, you can't. Are you canceling the n's?
You can do direct comparison.
Not direct. Now I will look at the high power terms. The high power terms are n and n squared. So I will compare this to n over n squared, which is 1 over n. That diverges, right? But this is never mind. This is a larger denominator, which means that series is less than a divergent series. That's inconclusive. We want to be bigger than divergent or less than convergent. So since direct comparison failed, direct comparison fails. We could go limit comparison, but kind of like I said earlier, that plus 4 is really insignificant. It's not going to be enough to change the behavior. And so this is still going to diverge, even though the direct comparison was inconclusive. But the absolute value diverges. The absolute value diverges. So now we have to go the alternating series test. Is the limit as n goes to infinity of n over n squared plus 4 equal to 0? And the answer is yes. Now here's the tricky one. Does it decrease? Is n plus 1 over n plus 1 squared plus 4, is that less than n over n squared plus 4? What do we think? It's a little bit harder to tell. My gut's telling me yes, but the problem is the numerator and the denominator are larger, right? If only one was larger, then we would have a conclusive answer. So this one, we would actually need to go through a little bit of algebra. If you, we're not going to have time to finish this. The answer is yes. I do know that it is going to be conditionally convergent. I would need to do a little bit more algebra, which would involve expanding the denominator here, multiplying by the common denominators and comparing sides. And it does work out. But for the sake of time, we're not going to be able to finish that in class. I will record myself working the others in great detail. And your homework is to do those other 4 and just hang on to that purple sheet of power series notes. We will do that at some point next week. Thanks.
Can you grab me my mistake?